Okay, so the second question I'm going to work on is going to be the rolling question. Now, for the rolling question, you can see that the set of the equations we had is going to be 19.1, which is going to give you the draft value. The draft is the amount of the reduction we're going to have in the plate after the rolling process. So it's just simply the initial thickness minus the final thickness. That's it. Initial thickness minus the final thickness. Now we're going to continue with that. Let's see what other calculation we can have here. The ratio or the reduction ratio is going to be the draft divided by the initial thickness. Now, away from all the equation we're going to have here, the strain is going to be equal to the length of the initial thickness over the final thickness, 19.6. You can write down that on your paper. Now, the flow stress. It's not going to be a flow stress. This one with the bar at the top of it, let me just zoom in for this one. Sorry. If we're going to have bar on it, we're going to call it the average flow stress. It's going to be average flow stress instead of the flow stress like what we have in the case of the forging. Now, there will be a possibility to have a question just to ask you what would be the maximum draft we can have. So the maximum draft is going to be equal to, it's not M actually, that's the coefficient of friction square multiplied by the radius of the roller. Okay, so it's going to be the coefficient of friction square multiplied by the radius of the roller, and the unit is going to be in millimeters. The force is going to be equal to the average flow stress multiplied by the width multiplied by the L. L is not just simply the length, it's going to be a value that calculating the length from this point to that point. And to do that, we have an equation here to do this calculation. So it's going to be the radius of the roller multiplied by the draft under square root. We have an equation for the torque, and we have an equation for the power. So once again, that's another equation, question, but again to use the PowerPoint to do the calculation again. Just let me prepare the question on my PowerPoint. Okay, now let's start to do our calculation. We have an 11.2 centimeter thickness stab. So this is the TO. Okay, that is 22 centimeter wide, that's the W, and 60 centimeter long. That's not the L we want, that's the length. It's to be reduced in single pass in a 2-height roller to a thickness of 9.6 centimeters. So that's the T final. The roll rotates at the speed of 5.5 revolution per minute. That's the N capital. And it has a radius of 42.5 centimeters. That's the R capital. The work materials has a strength coefficient of 205 megapascal, that's the K. And strain hardening exponent of 0.15, that's the N. We need to find the roll force, the roll torque, and the power required to accomplish this operation. So now in this question, we don't have the value for the coefficient of friction. And that means we cannot calculate the draft. But let's do it here manually. If I'm going to give you that the mu value, what's happened? Mu value is equal to 0.15. So we can calculate that the D maximum is going to be equal to the mu square multiplied by the R. Sorry. So let me take my calculator out and I'm going to do the calculation here. So we do have this one is 0.15 square and multiply it by the 42.5 millimeters, and the answer is going to be 0.95. So the maximum draft I can get is 0.956 0.956 millimeters. Now let's see the actual drop we have. I think that with the 0.15 is not going to work. So the draft we have here is 11.2. Oh no, wait a second, I did a mistake here. Sorry, 0.15 square times the 42.5 times 10. Yep, so we can get 9.56 millimeter is the maximum reduction we can have in single pass with the coefficient of friction of 0.15. Now let's try to check what will be the value for the draft we have. So we have 11.2 minus 9.6. Okay, and times 10, so we have something like 16. So with this coefficient of friction, it's not going to be done. So let's drop the coefficient of friction here to be 0.1. We can do that simply by adding some oil as a lubricant to make the operation look better. So now let's check this one once again. So it's going to be 0.1 square times the 42.5. Okay, times 10, so we can have 4.2. Again, what's happening is that the metal has been slipped, so we need to make the value for the coefficient of friction higher, so there will be no slipping and we can pull the metal much easier through the process. So 0.25 square multiplied by the 42.5 equal to, and then I'm going to multiply that by 10. Now I can do 26. The required was 16. So with the higher coefficient of friction, I can do a better draft because the part not going to be slipping between the rollers, and thus we are going to have a better value for the D maximum. So that's what's happened. I give you three different values for the coefficient of friction. We made it as 0.15, 0.1, and 0.25, and we found that the higher is the better. Now let's check about the other stuff like the roll force. So we start to calculate the draft is 1.6 centimeters. The L, we know the R multiplied by the draft, and then put it on the square root. We're going to get the value of the L to be 8.25 centimeters. This strain is the TO over the TF ln, and we get the value to be 0.154. This is the maximum strain we can achieve. Now calculate the average flow stress. That's the K. That's the value for the strain up to power n divided by 1 plus n. That's the equation that we show here for the average flow stress. Okay, so it's going to be the K mu up to n plus 1 plus n. Oh, just need to minimize that. Okay, so we calculate the average flow stress, and then we can find the value for the force. The force is equal to the average flow stress multiplied by the width multiplied by the L value calculated, and this will be equal to 2.5 million Newton. That's rolling force required. Now the roll torque, and I think that I'm not going to give you the question to ask to find the torque, but anyway, if I know the force, I know the L, multiply them by each other, then multiply it by 0.5. Okay, the Newton meter is going to be the units for that. Now we need just to calculate the value for the power, and the power is going to be related to the torque and the velocity. So the velocity we have was 5.5 revolution per minute. That's given in the question. And we need to change that to omega, which is radian per second. So we're going to have that the power is equal to 2 multiplied by the torque multiplied by the omega, or the force multiplied by the L multiplied by the omega. The 2 because we have 2 rollers. So the omega is rotational speed in radians per second, and it's going to be equal to 2 pi divided by 2 pi multiplied by n. And thus we're going to get the value of the power to be equal to 712.57 multiplied by 10 up to the power 4 Newton meter per minute, which is the unit for the watt. Okay, so or Newton meter per second to make it in a watt. Actually, it should be Newton meter second. Sorry, not minute. Okay, so thus we found the value for the power required to make the rolling process. So the next question is going to be about the sheet metal working. I'm not going to cover the extrusion now because, to be honest, this may not going to be a part of your quiz.